Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 196. And this episode is with the brilliant Stephen Wolfram, who is the founder and CEO of Wolfram Research, the creator of Mathematica, Wolfram Alpha, and the Wolfram Language. And among his many other accomplishments, Stephen received his PhD in theoretical physics from Caltech when he was only 20 years old, with the renowned physicist Richard Feynman on his committee. This is Stephen's second appearance on the show, much to my delight. And in episode 102, we talked about artificial intelligence, ChatGPT, and then there was a lengthy and enjoyable digression into the philosophy of math. In this one, though, we turn to another of Stephen's ambitious projects, which is his search for the fundamental theory of physics and how it has led him to a very mysterious structure called the Ruliad, which is the entangled limit of all possible computations. That's a mouthful, but we'll get into that in a lot more detail. And Stephen believes that the Ruliad, though I don't want to put words into his mouth, so these are my words, is the universe, or that the universe is part of the Ruliad. And observers like us are simply embedded in the Ruliad and experiencing it in different ways. We also, along the way, get into some ideas in the philosophy of science, some metaphysics about abstract and concrete objects, and then the foundations of quantum mechanics. A lot of the material that we discuss can be found in Stephen's book, A Project to Find the Fundamental Theory of Physics, and in writings on his website, including an article titled The Concept of the Ruliad, links to which are in the description. He also does plenty of live streams, he posts plenty of other articles. There are Q&As, so there's also a link to his website where you can find all of these things. On my end, reviews, likes, comments, subscribes, these are all very much appreciated. And there is also now a Patreon, a link to which is in the description. If you are interested in supporting the show, ad-free episodes, there's an RSS feed to that, and then some very nice show notes and takeaways. But now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with Steve. Before we get to the Ruliad, I want to start a bit with its history, which I guess is also your history. And my understanding from talking with string theorists, causal set theorists, loop quantum gravity theorists, is that many other theories of everything have come out of quantum gravity, since general relativity and quantum field theory are our two best physical theories. But my understanding is that the Ruliad did not come from this direction at all. So where did your search for the fundamental theory of physics begin?
Well, it's a complicated story. So when I was a teenager, I was interested in physics, and I became a pro before too very long, and I worked on quantum field theory and general relativity, basically, particle physics and cosmology and so on. And that was in the late 1970s. And at that time, I wasn't in the let's find a theory of everything. I was in, we have some theories, they're starting to actually work. Things like QCD, things about the early universe and cosmology and so on. Let's figure out the consequences of these theories. And that was a fertile thing at that time. And it was, I managed to make some progress on that. Then I got, I was making computational tools that I used. I don't know why other people didn't use them, but at least at the time, there were these computational tools for doing calculations in mathematical physics and so on. I used these to great effect. Then 1979, I kind of realized I had outgrown all existing computational tools, and, next step was build my own. So I started doing that, And that led to this thing called SMP, which was kind of a forerunner of Mathematica and Wolfram Language. And in building SMP, I kind of was I want to make this computational system. Think about it like a natural scientist. What are the kind of primitives of computation from which we can build this? And so I did that, built the system, practical system, et cetera, et cetera, et cetera. And then I got back into doing basic science. This is probably 1981 or so. I had this basic question about sort of where does complexity come from in the universe? And that the sort of the standard mathematical physics that I knew didn't tell me much about that. Well, I realize, and this is sort of back projecting history, because at the time I wouldn't have explained it this way, but the thing I realize now is that the experience of building this computational language, SMP, back then, from sort of these abstract computational primitives, kind of gave me the meta idea that you could just sort of construct a theory from nothing, so to speak, that you could construct a theory sort of from the ground up, rather than doing what one traditionally does in natural science, which is just to say, look at the universe as it is and try and say, how does one reverse engineer the universe as it is? So that kind of experience of building this computational system from sort of abstract primitives was the thing that kind of got me into this idea of let's see what happens when we just start from some abstract primitives and build things from there. What do we get? Do we get something that's like the natural world? Do we get something completely different? And then the big kind of set of discoveries that I made about these things called cellular automata that are just, simple rules applied to grid, with lines of black and white squares and so on. The big surprise was if you just do the computer experiments, you just sort of turn your computational telescope out into the computational universe, you discover some remarkable phenomena. Particularly, you discover that even when the rules are very simple, the behavior is complicated. And so that, to me, at first, that was a story of the explaining things in the natural world. How does one explain sort of the complexity of snowflakes or of turbulence in fluid flow? What are the underlying sort of foundational ideas, the kind of sort of pre-physics, sort of abstract ideas that lead to this? It's not traditional mathematics. It's not traditional mathematical physics. It's something different. I realized, was this kind of computational foundation. So I worked on that for a number of years. Then I had a sort of attempt to build what ends up getting called complexity theory as a sort of as an actual activity in the world. And the process of doing that convinced me, okay, plan B is just figure out a bunch of stuff myself. Let's not wait for the rest of the world to do this. Let's just figure it out myself. And that led me to start building Mathematica and Wolfram Language and our company. And also, in the end, this big book, A New Kind of Science, that I would now describe as being, at its heart, it's a work of ruliology. It's given these rules, what happens in the world? And the big surprise there was that sort of given these rules, given very simple rules, there was just a lot of richness in what happened and a lot of general principles like the idea of computational irreducibility, the principle of computational equivalence, and so on, these kind of emergent general principles that I kind of realized were there from having done this kind of essentially, natural history study of ruliology, of kind of what do rules out there in the computational universe do. Anyway, one of the use cases for this kind of new kind of science based on sort of thinking about things computationally, one of the use cases that I couldn't avoid looking at was fundamental physics, because after all, I knew a bunch about fundamental physics. And the obvious question was, you can see that from such a simple rule, you can get all this complicated behavior. So now the question is, well, what about the universe? That's our sort of biggest example of sort of complicated behavior. Could it too be the result of some very simple rule? Well, the first thing I knew was that cellular automata weren't going to do it. That was what we know from relativity about the structure of space and time and so on. Cellular automata say, let's start off assuming we know that sort of things are laid out in space in a particular way, that they sort of update in time in a particular way. We've already locked in the structure of space and time as this kind of grid, and that's not how the universe actually works. Actually, I recently learned that back in the early part of the 20th century, well, I knew that many physicists believed that, for example, space was discrete at that time, but I think Heisenberg in particular had a model of kind of discrete cells in space that's very much like a cellular automaton model, and he didn't manage to make it work. And the fact that he didn't had some interesting historical consequences. But I didn't even know that had been done by him at that time. But anyway, that wasn't going to work. So early 1990s, I'm sort of thinking about this kind of thing. And the big idea at that time was the realization that a network is a much more flexible structure from which you can potentially build space than this sort of fixed grid. So that sort of a technical thing, it's like you imagine that space is made of just discrete points, and the only thing those points sort of have to say for themselves is how they're related to other points. So you're building up this kind of network of relations. And then the result that I knew by the mid-1990s was much like when you look at a fluid with a bunch of molecules bouncing around, what emerges from that molecular dynamics on a large scale is fluid dynamics, is kind of the large-scale features of fluids. I knew that what emerged from sort of the small scale of this network and updates in the network and so on, what would emerge on a large scale with all sorts of sort of footnotes was general relativity, the structure of space and time as we are familiar with it from 20th century physics. So that was kind of exciting. I didn't figure out quantum mechanics at that time. I had ideas about it. I was frankly prejudiced from my own sort of desire, I suppose, to believe that sort of the progress of history is somehow unique, and that there weren't lots of copies of us all over the place doing different kinds of things, and I didn't really see how that worked. So then it was sort of my friends in physics at that time were like, we hate the fact that you're going after this completely different idea about how fundamental physics might work from the mathematical physics that we've all been doing for the last, 50 or 100 years. And so I was like, okay, fine. The market doesn't want this. I'm going to go off and do other things. So I worked on Wolfram Alpha and computational language and all sorts of things like that. 2018, I guess, I kept on coming back to thinking about this kind of, what could one make progress with in fundamental physics? The thing that then happened was I sort of realized that there was some things I didn't like that were kind of arbitrary in the way that I'd set up these networks and things. I made some progress thinking about hypergraphs instead of ordinary graphs and so on. That helped sort of unlock various technical aspects of things. Then 2019, a couple of young physicists who knew about what I'd been doing were like, you can't just leave this project undone. You've got to go forward and actually do something with this. And so that led to something that went vastly more quickly than I expected in 2019 of building up our physics project and actually understanding about how quantum mechanics works. And turned out the thing that I was afraid of doesn't actually happen for reasons that I did not previously foresee. But okay, so how does it work? This is a long tangled tale. I mean, the sort of big, the next big sort of injection of kind of confidence building was the fact that we seem to be able to reproduce the main features of 20th century physics from this underlying completely abstract infrastructure. But then there was still a problem, because the problem was, I thought at first we're searching for the fundamental rule, the fundamental computational rule from which our universe comes. But that always bothered me, because it's like we get to that, it's kind of the end of Copernicanism in some sense. We keep on being told we're not special. Our planet isn't the center of the universe, et cetera, et cetera, et cetera. So then if we find this rule, and it's one particular rule, we can hold it in our hands, and maybe it's a rule that seems to us simple, why did we get the simple rule universe and not some completely different universe? So that really bothered me for a long time. And as is usually the case with these kinds of things, that, it's like, I don't know how I'll explain that. It's kind of like when Newton was doing sort of celestial mechanics, was saying, well, once the planets are set in motion, I can work out what happened. But, how did they get into their initial configuration? That's the work of God, so to speak, was what he said at that time. Same with Darwin trying to figure out, sort of the natural selection, but how did the first life come about? In both of these cases, what we know from sort of the long run of history is that sort of it was a thing from outside the systems that they were thinking about that led them to eventually led people after them to be able to understand, how could a solar system form, et cetera, et cetera, et cetera. So in this case, the thing that we realized was that this idea that you're searching for the rule, and then you have to say, well, why this rule and not another? It's just not the right question. What's really going on, I think, is that all possible rules are being run. Now, we had a big tip-off to this because in this network, and the network is continually getting rewritten, and you're getting a new network at every moment in time, there are many different ways that rewriting can happen. And that leads to many different paths of history where you've got this network, it can be rewritten one way, it can be rewritten another way. Those are two different branches. After a while, the ways that it can get rewritten may end up with the exact same network. Two different branches may end up producing the same network. So then you have a merge in this thing we call a multi-way graph, which is this kind of graph of the possible histories of the universe. Not possible, the graph of histories of the universe. And so the first big tip-off is that we're not looking for the history of the universe. We're looking for this graph of these different histories of the universe. And in some sense, this sort of I suppose, ontological sort of view of this is they're all happening. It's not that we picked a particular one, they're all happening. And then the realization is that as observers of the universe, our minds are also doing this kind of branching and merging that the rest of the universe is doing. So this kind of, how do we perceive the universe? It's the story of how does a branching and merging mind perceive a branching and merging universe? And that story ends up essentially being the story of quantum mechanics. And it's so kind of this idea that we are an extended thing with respect to what we call branchial space, the space of possible branches of history. So that was kind of the realization there. Then we realized, well, but you can take this even further. Rather than taking a particular rule and applying it in all possible ways, let's just consider all possible rules. Now the question is, so how do we perceive the thing you get from studying sort of the evolution of all possible rules? You might say, how can you say anything definite from a thing where all possible rules are happening? Well, it is in fact a very rigid structure. You might think it's a big floppy thing because everything can sort of, in some sense, everything can happen, but there is a dynamics to it. It's not as if everything can sort of happen all at once. It's that there is, this thing happens, then that thing happens. There is a chain of causality about what happens. And yes, it's sort of all possible chains can be followed, but there's still a sort of a very rigid structure to this whole system. And so then and that thing, that sort of entangled limit of all possible computations is what we call the Ruliad. And so now the point is that what one has to think about is, if that's what there is in some sense, what do we perceive about what there is? Because we are part of the Ruliad. So the question of what we perceive about the universe is a question of how does a certain kind of observer of the Ruliad. We're not observing the whole Ruliad. We are observing some tiny little piece of the Ruliad. It's very much like in physical space. We're sitting on this particular planet, in this particular corner of some particular galaxy. And so our perception of the universe is based on that particularity of where we are. And there isn't really a theory of where we are. We are where we are. We can go and trace back and say, well, our galaxy evolved in this or that way. But, once we know where we are, so to speak, then we have a certain perception of the universe. And the point is, the realization is, it's the same story with the Ruliad. That is, we as observers are sort of, we are taking a particular tiny slice of the Ruliad. Now, the big question is, so can we say anything sort of scientifically based on this? And the thing that I realized is that the key observation is that it depends on what kind of an observer you are. If you were an observer outside the Ruliad, observing the Ruliad from the outside, if you could do that, you would have some conclusion about how complicated the universe is. But actually, we're observers with some very particular characteristics. For example, we are computationally bounded. Our minds are sort of, we have finite number of neurons, 100 billion neurons, whatever it is. We're bounded in the computations we can do. And we already know, I studied a bunch, the second law of thermodynamics, law of entropy increase, and so on. And that's a case where what we observe is that all those molecules bouncing around, they seem to us random in the motions that they have. Now, if we were to trace molecule by molecule and trace all the computations about how all the molecules interact, we would say they're not random. They follow very particular rules, and we can work out what they are. We can work out what the molecules will do. But the point is that as computationally bounded observers, we can't do that. So we kind of have to throw up our hands and say, it looks random to us. And that's sort of an example of how being an observer of the kind that we are necessarily leads us to certain conclusions about the way the world is. That is, we believe in the second law of thermodynamics because we are computationally bounded observers observing this kind of irreducible computation of these molecules bouncing around. And so that then leads us to the question of, well, given certain assumptions about us as observers, what does that mean about the physics we can perceive? And I think there are two key sort of features of us as observers, although I think there are other ones that seem so obvious that they've never really been called out as assumptions about how the world works. But the two that I think are critical for 20th century physics, at least, one is that we're computationally bounded, and the other is that we believe we are persistent in time. So it is not self-evident that we believe that there is a consistent thread of us that goes through time, even though in this model of physics, at every moment we're made of different atoms of space and so on. Even despite that, we believe that we persistently exist through time. Well, it turns out that those two assumptions, computational boundedness and persistence through time, those two assumptions with the mathematical structure of the Ruliad are sufficient to give us the three fundamental theories of 20th century physics, which to me is completely remarkable. Mm-hmm. Because the fact that it is possible to derive laws of physics is something that is at some level very surprising. I mean, the three kind of fundamental laws that we're talking about that are the cornerstones of 20th century physics are statistical mechanics, where the main event is the second law of thermodynamics, general relativity, theory of space-time, and quantum mechanics. And what has been believed in the past, what was believed from the 1860s on, is that, look, statistical mechanics, the second law of thermodynamics, should be derivable in some way from the laws of mechanics. Once you know how all these molecules bounce around, it should just be a matter of pure mathematical derivation to show that they satisfy the second law. Nobody's succeeded in showing how that works. In the end, I think the reason is that to understand it requires understanding about observers and computational irreducibility and computational boundedness and so on, which is a rather different kind of set of concepts than people were pursuing in mathematical physics. But the thing that is then very surprising is general relativity and quantum mechanics. Both of these were seen by me, as well as everybody else, as kind of wheel-in features of the universe. That is, we could have had a universe that has general relativity. We could have had a universe that doesn't have general relativity. Likewise, quantum mechanics. But what seems to be the case is that for observers like us, it is inevitable that what we perceive must be a universe which has those particular laws. So now you ask, well, what's the foundation of that? I mean, the Ruliad, in some sense, it's a necessary object. It's not an object that is like, well, it happens to be this way. It is sort of as necessary as the fact that 2 + 2 = 4, given our definition of what 2 is and what plus is and so on. That's not something we can wiggle out of. That's not something we can say, well, on Mars, 2 + 2 might not be equal to 4. given our definitions, it is inevitable. And so similarly with the Ruliad, given the kind of the concept of computation, the abstract concept of computation, the Ruliad is a necessary object. Strangely, it's an object, and it surprises me as well as other people, that it hadn't been studied before. It's an object that, in some sense, is an obvious object to consider. I think the reason it wasn't studied, certainly the reason I haven't studied it, is because, in a sense, computation, well, in my lifetime, computation has been gone from being super valuable to being somewhat everyday. But the profligate wasting of computation done by the universe is something that it took me a while to kind of come to terms with. That is that there could be, all of this computation happening that is all irrelevant it's all way below anything that we perceive. And that was and that there are all these different branches of history and different rules being followed and so on. And that sort of the universe is just doing all this computation was something that seems, it felt like, well, actually we should concentrate on the particular computation that we care about. But in any case, I think I think you're right that the Ruliad is sort of in its origins is not a reverse engineering natural science effort. It is a bottom up effort of, this is an abstract object. Does it now relate to what we see in the world? And as I say, in my personal history, the fact that I ended up thinking about science in those terms is a consequence of the pure coincidence that, I worked on sort of building computational tools for which I had to think about things sort of from the bottom up, after I happened to learn about a bunch of things about sort of top-down natural science.
Mm-hmm. Well, that was wonderful. My hope, and I'll give you a break now. My hope with this time is to get pretty deep into Ruliology, which is a new word for me. You've already taken us there and presaged a lot of the things that I wanted to discuss. Before I go on, though, maybe I ought to I have this quote here. It's basically a slogan, just to get maybe a sort of definition of the Ruliad on the board for our listeners. And so you wrote that the Ruliad may be defined as the entangled limit of everything that is computationally possible, i.e., the result of following all possible computational rules in all possible ways.
Yes.
But now, returning to what you were saying, I'm not a philosopher of science, but like most people, I've read The Structure of Scientific Revolutions by Kuhn a number of times. And what really struck me about what you were saying is how closely this story sort of mirrors his picture of revolutions in some ways. So you started out working in normal science, so to speak. We already had these established programs, general relativity and quantum field theory. And my understanding is that this is really where some of the other theories of everything emerged from. So string theory
Absolutely
comes out of modeling the strong force, so on and so forth. But then, and then the path integral is a key part of causal set theory. But then a young person comes along, and of course you were well versed in these theories, but you throw it all away. And I think your words were, you realized that you could construct a theory from nothing. And this is like the revolutionary effort. And the normal scientists do not like this. And as you put it, like a lot of people hated that you were going off and doing this in a completely different way. I don't know if I have the book on my shelf. I don't know if it was in a project to find the fundamental theory of physics, or it was in one of your posts on your website, but there was this really funny cartoon where a dragon with cellular automata for teeth is about to chomp down on a physicist who's writing equations in a blackboard. And I think this came out around the time A New Kind of Science came out.
I just looked at this again when we were working on the physics project, and I was kind of trying to explain its background. It was a review of A New Kind of Science in the New York Times. Mm-hmm. It was actually a very well written review and a sensible review by a journalist. But I hadn't looked at this for 20 years, and I'd completely forgotten what was in it. But the thing that, and at the time, I was like, why would my friends, the physicists, they might not care about what I'm doing. Why would there be any kind of negativity about it? And then I'm looking back 20 years later at this cartoon and, realizing that from the outside, from the point of view of this journalist writing this review, it seemed obvious to him that what this was, as you put it, the dragon, about to eat the sort of mathematical physicist. But I think, it's a funny thing because, for example, our physics project and now what's led to the Ruliad and so on, there are a whole series of sort of personal, circumstances that led to that path being a possible path, any one of which, had they not been there, that path simply wouldn't have happened. And, the fact that I've sort of alternated between doing basic science and doing technology development, the technology development drives this desire to kind of understand computation at a fundamental level for practical reasons. It's a somewhat strange kind of set of circumstances. And I think you're right that the traditional, physics went through a big kind of transformation in the early part of the 20th century. And that transformation was a lot of paradigmatic change. After that time, there wasn't a lot of paradigmatic change. There was a lot of difficult technical work, but it was within that established paradigm. And it's, I think the fact that we have my own efforts, had somebody said to me when I was in the middle of doing these things, are you sort of purposefully inventing a new paradigm? I would have said, absolutely not. I'm just, pursuing things using methods and techniques that I understand. What happened as I was writing my book, A New Kind of Science, I did realize somewhere in the middle of that, gosh, this is a different approach to science. Yeah. That actually wasn't my, initial take on things. But that was, in a sense, what I realized was that in the sort of the long view of sort of history of science, there'd been a long period starting in the 1600s when mathematics and sort of things like calculus were the dominant way of explaining things in nature. I mean, there had been methods from antiquity just saying this is what things are made of. But then we had the sort of mathematicization of exact science. And the question was, well, is there more, so to speak? And this was a realization, yes, there is more. And in a sense, it was a thing that was obvious given the ambient technology of our time, namely, computation, that doing mathematics, it's sort of ironic that I've, spent lots of effort sort of making mathematics doable by computer. And yet, in a sense, the bigger picture is the computation, not sort of this specific corner of it that ends up being the mathematics that we've currently done.
Mm-hmm. In our last conversation, we talked a bit about the formal mathematical dimensions of the Ruliad and how it connects to mathematical logic. But I wonder if you think that maybe one way of putting the crux of this paradigm shift in how science is performed goes back to something you said earlier, but it's sort of an adoption of a formal mathematical framework, the way people do formal math, where computational theory has its home, where, as you put it, though, physics is derived. Laws of physics are derived rather than being reconstructed based on experiment, the way that it has been done in the past.
I think it's worth realizing that it's a funny difference of paradigms between mathematics and physics. I mean, we could do axiomatic physics. We could say, here are a bunch of experiments. We don't care what's underneath. We're just going to figure out, how to piece together one experiment and another. In mathematics, we are doing, we often have thought of mathematics as an axiomatic business, where we simply say we put down these particular axioms and then we see their consequences. We don't necessarily, in physics, we think there's a there. We think there is a physical universe that's sort of underneath the things that we observe. In mathematics, the prevailing view from the early 20th century had been it's just you make up your axioms and then you work out their consequences as a purely formal kind of thing. And I think the thing that I sort of realized is that but this process of working out the consequences of axioms is the same kind of process as this process of figuring out what's going to happen in the physical universe based on sort of these abstract structures and the particulars of, you've got sort of kind of symbolic expressions versus you've got hypergraphs. None of that matters. It's kind of all a big bucket of equivalent things. And what's really going on in mathematics, as in physics, is that you are, to derive one theorem from another, you are sort of applying rules to get from that one theorem to the other theorem, just as in physics, you're applying rules to get from one state of the universe to another. So in the end, kind of the structure that you build, that is the kind of underlying structure of mathematics, is in fact the same structure. It's just this Ruliad structure. And sort of it's a weird thing because in physics, we're used to thinking about, for example, space in bulk. We're not personally, acquainted with the individual atoms of space. We don't give them names. In mathematics, in the sort of axiomatic way of thinking about it, we have things which are like the atoms of space. There's things even below axioms, but let's take the level of axioms. But we give these particular sort of points in mathematical space, we give them names. It's so-and-so's theorem or whatever else. We actually don't tend to think of mathematics in bulk. In the history of human mathematics, people have proved, a few million theorems. This question is, what is the limiting structure of mathematics? If we just went on proving theorems and we had a quadrillion theorems, what would mathematics be like? And there's sort of this, and both mathematics and physics are, I think, rooted in the Ruliad. They're both stories of what are the consequences of possible computations. The big difference between mathematics and physics is that the way we're sampling the Ruliad for physics is different from the way we're sampling it for mathematics. So in physics, we are these kind of computationally bounded observers, sort of progressing through time and experiencing through time. I think in mathematics, the better view of the mathematical observer, still computationally bounded, but instead of sort of a progression through time, there's more like, it's almost spatial, but not quite. There's sort of you're putting more and more theorems in your bag of things you believe. So instead of I'm experiencing the history of my life, I'm kind of progressively sort of putting more things that I believe are true into my bag of beliefs, so to speak. And that's kind of the sort of progression of mathematics looks like that. And there are all kinds of, you could ask, well, what are mathematical observers like? Can we conclude things about the structure of mathematics? Just as from the nature of physical observers, we can conclude things about sort of global laws of physics. Are there global laws of mathematics, for example? Mathematics, as we normally practice it, is a kind of theorem-to-theorem kind of business. Whereas it's not a thing where we make bulk statements about the structure of all possible theorems and so on. But in physics, we're not talking about physics at the level of individual atoms of space, or even at the level of individual molecules when we're doing thermodynamics, for example. We're talking about sort of bulk properties. And so there's sort of a question, what are the bulk laws of mathematics? The first bulk law of mathematics, I think, is that high-level mathematics is possible, which is not obvious. In other words, if you look at what, a proof-assistant system is doing, something, automated theorem-proving system, you say, let's look at mathematics at the level of really low-level axioms. Let's go all the way down to the sand and start trying to build up mathematics. Mm-hmm. That is a deeply inhuman activity. I mean,
right.
It
took a long time to find it.
Yeah, but it's something where the typical thing you do that, is it's made from tiny pieces. As a human looking at what's done by the computer, it's incomprehensible.
Oh, right.
And it's and I think and when you build up, if you want to build up something that humans might talk about and write on blackboards, you're talking millions, billions, quadrillions of individual little axiomatic steps.
Right. Humans can't read formal proofs.
Right.
Formal, like mathematical proofs that mathematicians use are so not rigorous compared to what a formal mathematician would take as rigorous. And even what they do is not at all what a computer would be reading at that
point. Right. So, you can build up the structure of a completely formalized proof, but it is way below the level of human mathematics. So, I think the analogy that's useful is to fluid mechanics, where there is a molecular dynamics. There are individual molecules bouncing around, but we humans do not experience that. We humans experience the overall flow of fluids and things like this. And so it is with mathematics, I think. I think that deep at that sort of foundational axiomatic layer, it's not what we experience. For example, we routinely will talk about the Pythagorean theorem. What do we exactly mean by that? What definition of real numbers are we using? What axioms are we using for this or that thing about set theory and so on? It doesn't matter. It's, we can still talk about the Pythagorean theorem, and we can do kind of human level, fluid dynamics level mathematics, just batting around features of the Pythagorean theorem without always grinding ourselves down and looking at the molecules, so to speak, looking at those sort of individual microscopic axiomatic pieces. And that, I think, is sort of the first sort of big law of mathematics, is that that's possible, that it is possible to do mathematics at the level of the Pythagorean theorem rather than at the level of the microscopic axioms of set theory and so on. You don't have to go down to that level. And I think that's a feature of sort of mathematical observers like us, just as physical observers like us believe in space, believe in thermodynamics, and so on. So it is, I think, that mathematical observers like us believe in kind of higher level mathematics. And it's sort of interesting because there are places where we run into problems with that. When we look at, when we run into undecidability in mathematics, when we run into Gödel's theorem and so on, those are places where we hit the edges. We can't look at things at the level of the sort of pure, the sort of fluid dynamics where we're somehow forced to look down to that lower sort of mathematical level. And I think that, that's a question, that sort of seeing down to the foundations of mathematics in a way that most mathematicians in their daily work, they just don't care. That's not important. And for a long time, I was very confused about why undecidability is so rare in mathematics. That is, we've known since 1931, there are theorems whose proofs are arbitrarily long, infinite, unprovable from a given set of axioms and so on. Why doesn't that, when it comes to figuring out the piece of mathematics that somebody cares about, why is there a finite proof of it? Because, for example, when you look in the computational universe of possible programs, many things you see there you run right into undecidability. Many questions you might ask, there's no finite computation that can answer them, et cetera, et cetera, et cetera. So why isn't this more common in mathematics? And I think the reason is because mathematics, as we practice it, is the sampling of the Ruliad done by mathematical observers like us, who, by the very nature of us as computationally bounded observers, have this feature that we end up sort of believing in this higher level, sort of fluid dynamics level mathematics. And that's sort of why it's because if we were different kinds of observers who were looking down at the level of those individual computations, we would be continually confronted with undecidability, as we are when we study sort of arbitrary things in the computational universe. But when we study things of the kind that can be studied by a mathematical type observer, we end up most of the time just being able to operate kind of fluid dynamics level without being forced down to this level where there's lots of undecidability. I think so. I mean, there's a lot of this. The thing that again is sort of, I think, perhaps philosophically interesting is this. Does mathematics exist in some sense? Is there a there for mathematics? And my belief nowadays would be that there's as much there for mathematics as there is for physics. In physics, we just have this intuitive sense that there is a universe out there that is sort of an objective thing that's out there. And, what one's saying is that, well, in the end, there's the Ruliad out there, but the sort of the way that the experiences we have are a consequence of the fact that we're observers of the kind that we are. Mm-hmm. And the same is true for mathematics.
You said just a minute ago, you said that you think this is philosophically interesting, and I can confirm that it is a philosophical gold mine. And I mean, this is a good example of how this new kind of science might require a new way of thinking, of doing, or thinking about philosophical questions. I mean, not just in philosophy of mathematics or philosophy of science, but in metaphysics and epistemology and all of these areas. But for the moment, though, I'd like to stick with science because there are some really big questions there and some big distinctions that I'd like to clear up. And the first is between theory and object. And I mean, I suppose one might define physics as it has been done so far as the study of matter and energy and the fundamental building blocks of the world. But there's a distinction between the theories that a physicist develops and then the world that they describe. But when I hear you talk, I hear about the Ruliad as an object, like the world or the universe or a multiverse maybe, but it also seems like it's our fundamental theory of the world in a way too. So the question is what the physicist is doing here. Is the physicist developing theories that describe the Ruliad, or is sampling and understanding the Ruliad sampling and understanding the theory itself, or do these things sort of break down?
It's sort of a question of what is science? What is natural science? Mm-hmm. And the way I see it is natural science is kind of a translation layer between kind of the underlying computation, the underlying world as it is, and the stuff that we can sort of talk about and think about with our minds. So in other words, what we've got kind of the things that are just happening out there, and we've got our way of describing what's happening. And I think that the fundamental role of natural science is to figure out, of all the stuff that's happening out there, what can we parse out that we can package in such a way that we can kind of have a narrative about it in our minds. I mean, there is something that's just happening out there, but the question is, what is it that we, how do we talk to ourselves about what's happening out there? And we are only sampling tiny pieces of what's happening out there. But I think to your question about sort of, I was surprised that I was able to say anything about this, but the why does the universe exist question, because there's, you can say, well, I've got this theory, but why is the theory actualized? In what sense, what breathes the fire into the universe, so to speak? What is, and I suppose and I don't know all the philosophical history here, but I certainly know the quote from Spinoza about, the universe is the thoughts of God actualized, so to speak. And it's kind of, it's this question of what is, how does one think about sort of what is actualization in a situation where what we somehow, and this real-time philosophy is a bit too hard, I think, but it's I know when my mother was a philosophy professor, which caused me to say that if there's one thing I'll never do when I'm grown up, it's be a philosopher. But one of the many things that I sort of would give a hard time to about philosophy was that the Oxford philosophers would give a talk and they would read every word of this talk, and it's like that's very wooden. You can do better than that. Mm-hmm. But actually, when you have to really, get all these distinctions correct, it's actually pretty hard to do that in real time. So but this question about sort of so I think on this question about sort of why does the universe exist, why is anything actualized, I think that the way to think about that is there isn't really a question of why the Ruliad exists any more than there's a question of why 2 + 2 = 4 exists, right? It's just an abstract thing. So now the real question is sort of then we have the sort of a priori knowledge that we are perceiving this thing. We are here perceiving this thing. It is in a sense less obvious that we should exist than that this abstract thing should exist. But in a sense, by the very fact that we're here doing the perceiving, we know that if we want to describe something as existing, we know that we're here, so to speak. And so I think that the kind of the why is there a I suppose it comes down to asking why is the universe why is there a perception of something like the universe out there that we have access to? And I think the answer would be that it is the Ruliad is this inevitable thing. Given that you know that we're here as observers, having a perception of things, it is inevitable that the things of which we can have a perception is this abstract object, because the abstract object doesn't. The abstract object is the only thing we have to argue. The only contingent fact, and even this gets more complicated. The only contingent fact is that we are computational and not, for example, hypercomputational. That is, the fact that we exist at a place in the Ruliad. So the Ruliad is sort of this entangled limit of all possible computations. Computation, something that follows rules. But as we start to say, what precisely do we mean by that? We might say follows rules like a Turing machine, or like a cellular automaton, or like a network rewriting system. Those are all equivalent. Those are all computations of the standard thing that we refer to as computation. But if we're just thinking about it, we can say, well, let's take things that are undoable in finite time by any computational system set up in this way. Let's just say we have a magic box that can do those hypercomputations, do in finite time computations that would take an infinite time for any computational system of the kind that we're describing. Let's say that we have a hypercomputational system. Well, then we could start building up a Ruliad from hypercomputation as well. We can build up a hyper-Ruliad. We can build up an infinite collection of hyper-Ruliads. So the question that is, again, not, I think, is a contingent fact about the world. Okay, there's going to be an interesting footnote to this, but the initial observation would be the fact that we are in the Ruliad and not in the hyper-Ruliad is something that is no more derivable than the fact that we're in this galaxy rather than some other galaxy. And it's just we happen to be here. That's the first level of I don't so much like that explanation. And as I say, I think, well, we're about to come to an even more bizarre point, which is, we say, well, what about, let's just go observe the hyper-Ruliad. Well, you can't do that. From inside the Ruliad, there's kind of an event horizon that prevents you ever having any kind of causal connection to things in the hyper-Ruliad. By the way, there's a whole hierarchy of these things. Within our universe, there are things that don't have all of the kind of richness of our universe, namely black holes. I wrote a piece about cats, so we'll have to talk
right?
about that. Yeah, right. Which is relevant to the Ruliad, but we'll get to that perhaps. In any case, the thing that's sort of interesting perhaps is we have our universe, which is sort of a computational kind of thing, and then we have things like black holes. And one feature of sort of the simplest kind of black holes is time stops. In other words, in our universe, we believe time just keeps going, keeps going, keeps going. But in a typical black hole with a space-like singularity, there's a time just stops. In our models, it's pretty easy to see how that works. There are these rewrite rules, and there's just no rules to apply. But the point is that what would, in our universe, would be this thing where we say, well, you can have arbitrarily long proofs, you can have arbitrarily long sort of experiences of the universe. If you are stuck inside a black hole, you don't have that. So similarly, from the point of view of the hyper-Ruliad, our whole Ruliad's worth of experience looks like a black hole. It looks like, gosh, you can't, it's not quite, time is finite in the same, well, time is infinitesimal relative to what can be achieved in all the time of our universe is infinitesimal compared to what can be achieved in a moment of time in the hyper-universe. And so so now one of the things, which is again one of these, so you say, well, we got the Ruliad, we got the hyper-Ruliad. Why did we get stuck in the Ruliad? Why didn't we have why aren't we in hyper-Ruliad number such and such? I'm pretty sure that there is a notion of Rulial relativity, that basically once you are an observer that has certain level of computational capability, that it is your experience of the world is necessarily the same. In other words, if you're an observer in any level of the hyper-Ruliad, you are, when you perceive things, you will, if you're in a hyper-Ruliad, then your perceptions are hyper relative to what they would be in our Ruliad. But if you are, but you match the level of Ruliad that you're in. And so I think, we still need to work out the details of this, but I think that it's going to end up that it doesn't matter, that there is no, that removes that piece of contingency, so to speak. But I'm not sure. Let's see. I forget how we got to this now. But we're talking about kind of the necessity of the existence of the universe. Why is it necessary that the universe should exist? And my claim is that these abstract constructs necessarily exist, and that the question of whether, I think I managed to get a bit further than this, and I'm trying to remember what all the arguments were here. But this question of whether, the issue is within the Ruliad, why is there a thing that is like an observer? Why should there be anything that is like an observer like us? And I think that, so one question is, what does an observer like us fundamentally do? And I think the answer is, what observers do is they take the complexity of the world and they try and stuff it into a finite mind. Because, there is all this stuff going on out there, but we don't perceive that stuff. We perceive this tiny trickle of information. We're, the photons falling on our eyes, there are zillions of them every second, but yet all we perceive is, I'm looking at a face or something. In other words, we are equivalencing, and the same thing in a much more physical setting. Imagine we're trying to measure the pressure of a gas, and we have a piston. We got some, and all the gas molecules are hitting the piston, and there's a zillion configurations of these gas molecules. But all that matters in measuring the pressure of the gas is what the aggregate force on the piston is. And so that measuring process is equivalencing a large number of states of the world. And I think that's the essence of a computationally bounded observer, is that you have to equivalence lots of states of the world to stuff your experience of the world into, a finite mind, so to speak. And so then the question is, you start asking, well, are there pieces of the Ruliad, are there pieces of what's possible that we can interpret as kind of a thing that is equivalencing things and sort of reducing them to something where we can where we can interpret it in this way. And I think it's one of the features, one of the sort of scientific facts, is this phenomenon that within any computationally irreducible system, there are necessarily an infinite number of pockets of computational reducibility. So to unpack that a bit. So given that you have a set of rules and you say, I'm going to run these rules, you might say, if we know the rules for a system, then we're done. We know how the system's going to behave. And that was what people sort of assumed was true. But it isn't true, because what happens is the working out of those rules involves a certain amount of computation, and it can involve an irreducible amount of computation. So if you say, I want to know what's going to happen a million years from now, it's like, sorry, the only way you can work that out is to live through those million years and do all those computations. That is not, the conceit of mathematics, in a sense, is you just solve the equation or you fill in the numbers in the formula and you're done. There is a quick way to work out what's going to happen. But the difference, the fundamental difference between sort of the mathematical paradigm for thinking about science, I think, and the computational one is in the computational one, you're given a rule and then you have to run it to find out its consequence. It's not you can just nail it and have something which is kind of finite mind narrative of this is the mathematical result. So there's this phenomenon of computational irreducibility. It is, I think, it is a really central phenomenon. I mean, it's if there's one thing that I think, is sort of a takeaway from lots of things that I've done, it's the idea of computational irreducibility, because it's what leads to, it has consequences all over the place. It has consequences for things like free will. It has consequences for, if there wasn't computational irreducibility, then the passage of our lives and the passage of time would not really mean anything, because we'd always be able to say, you lead your life, you live out many decades or whatever, but the answer is 42. You know the end. You can just jump to the end. The fact that we have to experience all of those intermediate steps is a consequence of the phenomenon of computational irreducibility. It's also in a quite different domain. If you're thinking about, AI, and you say, I'm going to put in these rules for AI governance and they're going to work perfectly. It's like, well, no, they're not, because there'll always be an unexpected thing that happens, because the working out of those rules will show computational irreducibility. And it's computational irreducibility is a completely ubiquitous thing among systems of rules. But the thing then that's surprising, okay, so given computational irreducibility, why is science possible? In other words, why is it possible to make statements about the world that are useful narratives for finite minds? You might say it's just hopeless. We can't figure out anything. The thing that is then a sort of a fact about computational irreducibility, it is inevitable that within a computational irreducible system, there'll be an infinite number of pockets of reducibility, of places where you can make a little prediction. And it's rather a fairly easy argument that if that wasn't the case, if it was sort of uniform computational irreducibility, you could use that very fact to make predictions. And so, that sort of diagonalish argument gives you this result. But then, so that means there are all these pockets of reducibility. What are those? What are those? Well, those are the places where those are what we live in. The fact that our universe is somewhat predictable is because we're looking at a slice of reducibility in all of this computational irreducibility that's throughout the Ruliad. We are sampling a piece of it. Observers like us sample a piece of it that represents a pocket of reducibility. And by the way, there are a lot of other things that those sort of pockets of reducibility correspond to. Like, for example, I think technology, scientific discoveries, technology. These are all examples of pockets of reducibility. The world's a complicated place, but we can make a scientific statement. The fact that science is possible because there are these pockets of reducibility, and that's essentially where the science lives. That's what the science is doing, is it's identifying, these pockets of reducibility. By the way, that has another consequence, which is science will never be finished. There are always more pockets of reducibility. It's not self-evident, I think. It could be the case that, if it wasn't for computational irreducibility, then we would say, we found the rules of the universe, we're done. But that's not correct because of irreducibility. But it's still going to be the case, even given the irreducibility, that we can say things and there'll be an infinite sequence of things we can say. I mean, it's the same thing with technology. There's a question of will there be a moment when every invention has been made? And the answer is no, because inventions are these places where you're getting sort of, you're making use of some pocket of reducibility. I mean, the footnote to that is, the one thing that could happen is every invention that we humans care about has been made. I don't think that happens because I think that the domain that we care about gradually expands. And I think that's, one thing a sort of a little bit of a whimsical way to talk about it, but, the progress of science and sort of the arc of intellectual history is a story of kind of, additional paradigms, additional ways to measure things about the world and so on. And the question is, if we look at our sort of presence in the Ruliad as a species or something, one aspect of our expansion is we send out spacecraft and they go a certain number of astronomical units away from us. That's exploring physical space. The growth of paradigms, I think, is a growth in Rulial space, that we're gradually sort of putting, there are more domains of, there's sort of more descriptions of the universe that we can put in our bag of things that we can stuff into our minds. So in other words, we're as we invent a new paradigm, we are able to sample, we're sort of exploring more parts of the Ruliad. We're exploring more different kinds of rules that we can use to sort of talk about the universe and so on. So so it's kind of a sort of the expansion of in our, we can make a choice actually. We can send out more spacecraft, or we can do more theoretical science, and or some more experimental science and find more different kinds of measurements that we can make. We start so these are,
we can move farther or get smaller.
Yes. Well, right. I mean, that's another issue. It's another very interesting thing, I think, about us as sort of a contingent fact about us as observers. We're actually pretty big. That is, if the universe is, 10 to the 26 meters across in physical space, and we're, give or take, a meter tall, we kind of think the elementary length, the effective distance between atoms of space or something might be 10 to the minus 100 meters. So relative to that, we're maybe, I don't know if that estimate is right, we're 100 orders of magnitude bigger than the smallest, and 26 orders of magnitude smaller than the biggest, so to speak. So we're pretty big. And there's sort of a question of, what's that?
Good for the ego.
Yeah, right. Well, okay. Don't get too confident there, because I think we're big in physical space. In the Ruliad, in Rulial space, we're pretty damn small. Mm-hmm. In other words, so one sort of way of probing that question, really the question of how big are we in Rulial space is the question of sort of what is the diversity of what different kinds of minds can perceive. If we are some point in the Ruliad, then with minds of the kind we have, and each of us has a different mind, so to speak, we're all these little points in Rulial space. Humans with similar kinds of, backgrounds or whatever might be quite close in Rulial space. Your cat there is a little bit further away in Rulial space. Although, we can recognize, certain features, the emotional, characteristics of the cat are sort of recognizable to us, even though cat philosophy is probably not something that, if there is a cat philosophy, we don't know what it is.
It's very tuna-centric.
Yeah, right. That's I do think that in modern times of machine learning, one of the things that, the talk to the animals thing should be a thing. The main block is this question of sort of the distance in Rulial space, the kinds of things that, that one might talk about may be so bizarrely different that they're not things where, it's like science. It's like this translation layer between, science is a translation between the natural world and what goes in our brains. And this is sort of a level of a science-like thing that is, the translation from what's going on in the animal brain to what's going on in ours. But I think, let's see, we were, yeah, right. So I mean, in, this question of how big is the space of possible alien minds? What is the diversity of possible ways to look at the universe? And I did a little experiment. It's a very, very, I would say, sort of very basic approach to that question, which is, think about an AI, and you're thinking about kind of a generative AI system, and the typical image generation AI system has been trained on billions of human-produced images, and then it's generating things that are like those human-produced images. And so you can start asking, well, that's a mind that's aligned with a human mind because it's trained from human-produced images. But you can take that mind and just start changing the weights and the neural network. And then you have something which is not quite like, it's started from a human mind, but now it's sort of modified relative to that human mind. And you can start asking, well, what are the images that you produce in that case? There's even a simpler thing you can do. You can just say every image that is generatable is there's this kind of latent space. There's this kind of sort of numerically defined, coordinatized space of possible images, so to speak. And you can just say, well, there's a particular region of that space that corresponds to a picture of a cat, and as we change our coordinates in that space, we'll make other kinds of pictures. And so then the question is, there are some pockets of that space that correspond to human concepts: cats, dogs, elephants, whatever, right? And the question would be, if you look at that whole space, what fraction of the space is covered by those human concepts? So, for example, one of the things that I made some pictures of is Cat Island, the thing which is near the concept of a cat. As you go further away, you see pictures that don't really look like cats anymore. And pretty soon they degrade into things that are not really recognizable by us humans as pictures of anything that we know about. So even in the simplest case, the region of, in a sense, Ruliad space, that there's a small, tiny slice of Ruliad space, but the region that corresponds to concepts that we are familiar with is about 1 part in 10 to the 600. So in other words, the stuff, the part of Ruliad space that we are familiar with, even in this very simple slicing of Ruliad space, is an absolutely infinitesimal fraction. What else is out there? I was referring to it as interconcept space. There is, dotted around the space are concepts that we humans have decided to invent so far in our sort of civilizational history. But in between those concepts, it's like interstellar space. There's things that we haven't explored yet, and those are huge compared to the ones that we have already explored. So in some sense, we are that's a. And by the way, I mean what we can imagine is that over the course of time, we will gradually bring into our kind of domain of knowledge more and more things that are sort of out there in this space. So an example would be, go back 50 years, we're making these pictures. Some things that show up in these pictures are nested fractal patterns. If you go back 50 years and you saw those things, you're just kind of just shrugging your shoulders. I don't know what that is. It's just something I don't really know about or care about. Now that we know about fractals and nested patterns, we immediately say, oh, that's a fractal pattern. And no doubt there are many other things out there in that space where in time, for whatever reason, we may start caring about these things. We may give them names in our human languages and so on. And then that may be part of our sort of domain of things we think about. I mean, it gives one, there's a sort of a funny twist, which I don't know whether I fully understand yet, which is, you say, well, what's the future of history? Well, it's kind of like we explore interstellar space and physical space and so on, and then we explore the Ruliad. We go on exploring more and more of the Ruliad. and kind of the story of intellectual history could be the story of sort of just expanding in real space. They say, well, then eventually we get to this wonderful situation where we've expanded throughout real space. We're done. We've discovered everything. The problem is, I think in that case, by the time we've expanded our mind to encompass everything, our mind is no longer coherent. We no longer coherently exist. That is, I think that the coherent existence requires sort of, in some sense, smallness. If you are everything, then there's no coherent you to the whole story. There has to be the fact that we have coherent minds that believe that we have definite experiences and things like that, I think is a consequence of the fact that our minds are not, they're limited, so to speak. If it wasn't for that, we wouldn't have this kind of coherent sense of being us, so to speak. And so I think it's kind of a be careful what you wish for situation, because yes, we just succeeded. We expanded throughout real space. Oops. The problem is now we don't coherently exist. I think that's I think that has all sorts of resonance with things people talk about in many kind of Eastern traditions and philosophy and so on, which are, I find it interesting how little I understand about those things, because in a sense, that's a story of one's kind of limitation in real space. And that, I've grown up in sort of a Western thought tradition, so to speak, and it's really difficult for me to understand, even if there is some there, it's, I with my way of thinking about things, it's like I try and approach it with my way of thinking about things, and it just doesn't quite fit. I mean, this particular point is perhaps a point of contact between these kinds of different sort of ways of thinking about things.
Well, these notions of exploring the Ruliad, of sampling the Ruliad, of the translation layer, I mean, it all just raises so many more classical questions in epistemology and metaphysics and the philosophy of science. And you said a while ago now that natural science is what we can parse about what's happening out there. And you also said, with regard to the Ruliad, I mean, it's this necessary abstract object, and that we have this perception of it. But where I'm getting at is that physics is generally considered to concern, quite naturally, the physical world. Physical or material, these terms, they get a bit murky when one starts talking about things like fields and wave functions and so on. But even though, physical objects like the computers we're using right now, they do carry out calculations and so on, but computation itself is an abstract process. And the Ruliad itself is, to reference that quote again, the entangled limit of everything that is computationally possible. So it's a collection of equivalence classes or something of that ilk. And so I wonder then whether ultimately you view the universe as a physical object or an abstract object, or these categories just somehow don't make sense anymore at this level of discussion, or whether we're physical.
I think they don't make sense, because I think that,
that's awesome. That's great.
Yeah. All I know is what I perceive. Mm-hmm. And, it's not to have the, you might say, and I know there are traditions in philosophy where one sort of gets oneself tangled up by thinking that way and saying there's no there outside, so to speak. It's a little different in what I'm talking about, because there is something there. It's the Ruliad, but it's not this question of whether there is is there a thing that makes, in what sense is, a solid object more real than some concept of mathematics? I mean, that's kind of the, and I suppose Yeah, I mean, there's this question about what's out there in physical reality. One of the things we've got to realize is that as we have progressed in the history of physics, we've had different kinds of measuring devices. There are things where they were presumably features of the universe all along, but we never knew they were there. And I think that's kind of that's the experience of saying, so in what sense is it even worth talking about a thing about the universe that we are completely unable to perceive? Is that you might still say, well, it's there, but we can't perceive it. And so it's not something that's going to be part of the canon of our physics. It could be that there are, gravitational waves. Okay, that's a thing that wasn't, that was a long expected thing. But there could be, all kinds of strange phenomena, that I could imagine, for example, in our models of physics, there are dimension fluctuations. Our universe, we think of it as three-dimensional, but actually, in our models of physics, it isn't exactly three-dimensional. It has little dimension fluctuations. And that's something that we are not currently, we don't have I don't know how we measure those. Possibly they're related to gravity. Possibly they're related to dark matter. But, once we get to the point where we suddenly realize, oh gosh, we can use this method to take these dimension fluctuations and render them in a way that sort of connects to our minds, then we've got a whole different set of things that we can talk about in terms of physics, and a whole different set of things that we can kind of say are, discuss as physical constructs. But I think it's a question of what is it that we can successfully perceive. Those are the things about which we're going to have a physics discussion. If we're not perceiving it, we don't, we don't discuss what we don't perceive. And there might be, and you say, well, there might be things where there's a little, there are a lot of things which in the history of physics, for example, things about quantum mechanics, where physics went along for years without ever caring about any of that stuff, until there started to be experiments which rubbed our noses in those phenomena, and which came about, I think, because of the electronic amplifiers and things like that got invented, and that allowed us to amplify small signals, and we could start to detect things we hadn't been able to detect before. But I mean, this question of it's sort of interesting as one starts to kind of, one of the things that's always challenging is to live the paradigms one invents. And, this is a thing which is, honestly, I think it's one of the more challenging things. It's like, as you have different generations of thinkers, it's usually a couple of generations later that people kind of can really sort of, the paradigm is so obvious to them that, you can sort of build on it. And I have to say that the kind of the perception of sort of this idea of the Ruliad, and the idea that all that is real is our perception of our particular perception of it, and so on. I'm not sure that I've totally internalized that. I mean, just to talk a little bit about personal history and the internalization of paradigms, it is interesting to me that, in my life at least, many kinds of ideas, they take a couple of decades at least for one to internalize it. That is, you see a phenomenon, the primary problem of doing things like experimental science and ruleology, just studying possible rules in the computational universe, is a kind of experimental science. The challenge of experimental science is to discover things you didn't expect. Because too often, your paradigm for thinking about things is one which makes you blind to things that you don't expect. And in fact, this phenomenon of complicated behavior from simple rules, people had observed that for at least 50 years, if not longer, before the things that I did. But they just ignored it. They said, oh, we're studying early neural nets, and sometimes they have noise, and the noise is a nuisance, and we want to study, how do they behave like brains that make decisions or something. But and it's even the case, when I was first studying these simple rules and their consequences, a number of very good mathematicians got involved in doing that, and they said, "This is, we're going to be able to solve this. These are simple rules. We're going to be able to crack this with mathematics." After a couple of years, they were like, "Nah, we can't say anything. We give up." Okay, and I suppose that the thing that, in a sense, I realized many years after the fact is my main intellectual achievement at that moment was to realize the fact that one was giving up was itself very interesting. I mean, the fact that there was a paradigm that was all about computational irreducibility and all these kinds of things that was orthogonal to the mathematical paradigm in some sense, or different from the mathematical paradigm, that was in itself very interesting. But it took, I would say that a lot of these kind of, a lot of these ideas, they take a surprisingly long time for one to kind of internalize, so to speak. I mean, and it's kind of the role, in some sense, of scientific history is to go back and look, because there are lots of things I can see from my own history where, for example, the fact that building this first computational language of mine was important in the realization that you could build a physics from nothing, so to speak. It took me several decades after that had happened before I realized that kind of intellectual connection. But I think, this question of what does it, if one now is thinking about the world in terms of the Ruliad and perceptions of the Ruliad and so on, how does that make one feel about one's experience of the world? And, it feels, and I'm at the early stages of understanding that. I mean, I think it kind of, I think it's sometimes easier to see the scientific consequences. I mean, there are broader consequences of things. I mean, like for example, if you look at sort of the big arc of scientific history, there are, one very dramatic moment in scientific history was sort of the whole Copernican revolution story, which one can interpret as being, it's obvious, before that time, it's like, we're on the Earth is still, is stationary, and we're looking at all these things moving around the sky, and it's obvious that the Earth is stationary. How could it not be? That is a matter of our common experience. And then, the surprise is you can make up a bunch of math that shows that the Earth isn't stationary, so to speak. And, it's better to think about it as going around the sun. And then it's like, okay, really, you've got to sort of switch off your common sense and say the math is going to solve the problem. It's going to be it's a different way of getting access to what's going on in the world. And I think that, and finally, after a few centuries, people got used to the idea of so we can calculate stuff. And then people got to this belief that, then we can calculate everything. We run science a bit longer and we can figure out, what's going to happen in this epidemic or what's this or that or the other. We can figure out everything just from, quote, science interpreted as this kind of jump ahead, we can make a formula for what's going to happen. I think the thing that, in a sense, if there is a broader significance to figuring out things about fundamental physics, it's that, in this picture, things are computational all the way down. And so just as one is forced by sort of the whole Copernican story to say there's a certain amount that we just have to figure out with math and we can't figure out from common sense, so one is forced by the idea that everything is computational all the way down to say, so the phenomena that happen in computation are ones that we have to confront. We can't say everything we do, yes, there is computational irreducibility in principle, but it's not going to be important for the things that, it's something that's just out there and not a thing that will be relevant to what we're dealing with. So, I think that's but I mean, you're asking this sort of question about, how does one feel about whether sort of there's a thing out there, and what is that thing? And one and I think this is more a question of humanly coming to terms with what is essentially an intellectual structure than it is a question of I think the intellectual structure is I like to think reasonably clear at this point. Now the question is, how does one come to terms with that intellectual structure? It's just like saying, at the Copernican time, it's like there's an intellectual structure that was, now we have to come to terms with. You just calculate it with math, which is totally disorienting. If you're starting from the look, it's obvious that the Earth is standing still, so to speak.
Well, talking about living with one's paradigms, another paradigm that you're very familiar with and that is notoriously difficult to live with is quantum mechanics. And I mean, it's one thing to accept that quantum field theory is so successful, and it's another thing to accept or really live, I suppose, concepts like entanglement, just to take a common example. And there are so many fascinating ways in which the Ruliad connects to or derives more explicitly interesting physics, like that of general relativity and black holes, like you mentioned a little bit earlier. But to focus on one for a moment, I'm curious about how living with these two paradigms, the Ruliad and quantum mechanics, has been for you. In that, I'm wondering if accepting the Ruliad forces a specific interpretation of quantum mechanics on you, because as I take it, the Ruliad is deterministic.
Yes. So I mean, okay, my old friend Dick Feynman always used to say, after spending his life studying quantum mechanics, one of his favorite quotes was, "Nobody understands quantum mechanics." Mm-hmm. And I think I am inching towards the point where I can say I actually understand quantum mechanics. I don't think I'm fully there yet, but I'm at least inching towards it. And I think the sort of key observation is this point about the many paths of history and the fact that we, in our experience, span those paths of history, span multiple paths of history. Just like we don't fill the whole universe, we don't span all possible paths of history, but we span a chunk of paths of history. And that's, in a sense, when we say there's, so then there's the question, okay, so that one of the issues is, why do we think that definite things happen? If there are many paths of history, why aren't we just living in a world where many different things are happening? And inside a quantum computer, I think that is what's happening. That's what a quantum computer, inside the mind of a quantum computer, it has many different things happening. The challenge with a quantum computer and the challenge of what happens in quantum mechanics is somehow you have to take those many paths of history and somehow aggregate them to something which is compatible with observers like us who believe that definite things happen. And so it's like a measuring device. It's like the molecules hitting the piston. All those molecules are doing different things, but the piston has one uniform kind of thing that it's doing. I think in the case of most kinds of quantum measurements, that it's more like a weighing balance. That is, it's, in the case of the piston, it's just aggregating real numbers, and it's eventually, this is the average pressure type thing. In a slightly different, but very similar kind of measuring device is a weighing balance, where there are many different ways you can put grains of sand on the two sides of the balance, but in the end, it will go to thunk one direction or the other. And I think that's similar to what's happening in the measuring devices that are used for measuring things like qubits and so on, where there's sort of this binary decision about was the spin up or down or whatever else. Now, if you then ask, so what, when you're thinking about sort of the rules of quantum mechanics and you're asking I think the underlying rules of quantum mechanics rather easily map onto this sort of underlying dynamics of these multi-way systems and many paths of history and so on that stuff is pretty directly the path integral.
Mm-hmm.
The issue is, can we explain why it's a discretized version of that, which is quite mathematically interesting, blah, blah, blah. But in the end, it's sort of unsurprising because it's kind of just like it's an actualization in some sense of the mechanization of things like the path integral. But then in traditional quantum mechanics, it's been kind of 100-year wimp out because it's just like, and then there's this idea of measurement. And we go from the quantum amplitudes to the measured result, and then something definite happened. And we haven't had to describe, the formalism of quantum mechanics has mathematically tiptoed around this question of how does the measurement actually happen? And in our models, there's much better chance to say, let's unpack what's inside the observer. What is the observer doing? The observer is taking all these different things that can happen, all these different threads of history, and they're equivalencing many different configurations. And they're saying, so the spin was either up or it was down. And now we get to start unpacking that and saying, well, what were the actual processes that caused that equivalencing to happen? Just like in the case of the piston with the molecules and so on, what were the processes? Well, every molecule that hits the piston causes the piston to deform a little bit. But, there are effectively sound waves in the piston that are exchanging momentum between the different places where it gets hit. And it's a rigid thing. And so pretty quickly it dissipates kind of the little deformations that come from the individual molecules. And then you have a sort of collective motion that occurs. And so similarly, and I haven't done this and I've been wanting to do this, is to really go through the sort of the details of how different quantum measurements are made mechanically, in the lab. What do you actually do? And, I know I've gone through in qualitative terms, and I think we can kind of trace that it's a bunch of equivalences that are being done. But then the question is, well, what can you say when you unpack this process of measurement? What can you then say about quantum mechanics? What additional things can you say? For example, will quantum computers work? Or is it the case that what you gain in having these many paths of history and many sort of parallel threads of computation, you'll lose but then you have to knit all these pieces together, and that takes a lot of effort. And I think that's an example of where you get to kind of make a finer statement about quantum mechanics. Now, you could ask, do we understand why the Born rule of quantum mechanics works? Not completely. We have arguments about it. We have arguments for why it should work. Have we dotted the I's and crossed the T's? Not yet. I am confident that that's going to work out. But we don't, it's just, this is one of the challenges. You have a very foundational theory, and you're trying to get it to the point where you can say, go do this experiment. I mean, there are lots of people who've said to us, we have this giant telescope. What should we look for? What actual experiment should we do to look for, let's say, dimension fluctuations in the universe as it is, or look for some other kinds of phenomena that our models predict. The problem is that actually going in and nailing down kind of, what the details of what the telescope should see are is a whole bunch of work. And it's a big stack of kind of mathematical physics and other things that you need to go through, and computational irreducibility is not your friend as far as this stuff is concerned. And, we're slowly getting there. We now have nice simulations of black hole mergers. We're starting to have simulations of quantum black holes and so on. But it's a whole bunch of work, and lots of people are getting involved in that, which is nice. But when it comes to, let's reproduce all. Okay, so I can say in terms of, I think the fundamental point about, quote, understanding quantum mechanics is this idea about branch shield space, this idea that quantum mechanics is, so for example, the fundamental law of quantum mechanics, you could state it in different ways, but a nice way is in terms of the Feynman path integral. And the path integral says that the amplitude you get out is this, you integrate over all possible paths, and you take each path is weighted with e to the I times this quantity, the action, divided by h bar Planck's constant over 2 pi. So it's a phase, and e to the I something or other, and the something or other is this action object, which is essentially an energy density. And so the thing that's really cool is what it's saying is the phase of the quantum amplitude is determined by this energy density-like thing. So in physical space, the thing we know is that the paths particles take in physical space are deflected by the presence of gravity. Gravity, the source of gravity is energy momentum, mass, energy momentum, whatever, they're all the same thing. So in other words, a path taken in physical space that path is determined by the presence of energy momentum. It's deflected by gravity. And so now we go to the same thing in branch shield space in this multi-way graph, and we're looking at, and what turns out to be the case is that the paths in branch shield space basically are also deflected by the presence of energy. Energy in our models is essentially the density of updates in this network. So paths in branch shield space are deflected by the presence of energy. And then I'm sort of skipping lots of pieces here, but basically our current belief is that position in physical space, we understand what that is. That's kind of our common experience of position in physical space. Position in branch shield space, we're pretty sure corresponds to quantum phase. So saying that the presence of energy momentum deflects paths in branch shield space and so on is basically saying the presence of energy momentum changes quantum phases, which is essentially what the path integral is saying. And so the belief is that what in physical space is the Einstein equations for space-time and gravity and so on. In branch shield space, it's the exact same sort of underlying process, but now it's the Feynman path integral instead. So this is, from a pure sort of elegance in physics point of view, this is quite spectacular because it means, general relativity and quantum mechanics, people have wondered how do they fit together. Well, the answer is they're the same theory, but they're the same theory played out in a slightly different space. And by the way, there are already echoes of that in what's been done in mathematical physics, the holography principles and the ADS-CFT correspondence and so on between sort of things in general relativity, things in quantum field theory. I think those are kind of echoes of the exact same phenomenon. That in some sense, these two theories are really the same theory. And for us, there's this thing we call the multi-way causal graph, which is the big graph where one projection of it is physical space, another projection is branch shield space. So in a sense, this graph encodes both quantum mechanics and general relativity, and you're projecting it in different ways to get sort of the experience of different things. So but let me give you one more kind of picture of sort of how quantum mechanics tries to work. So one of the things that's always confusing in quantum mechanics is things like destructive interference. So, you have two slits, you have, the photon can go through one slit or it can go through the other slit, but you say, well, it can go through either one or the other. So, by the time you're looking in the center of the screen behind these things, it's, there's got to be something there because after all, it could have gone through one slit, it could have gone through the other slit, but how can you end up with nothing there? How can you end up with destructive interference of the probability that a photon gets there? Okay, so here's what I think happens. And I think it's bizarrely similar to a phenomenon in mathematics, actually. Let me actually explain the phenomenon in mathematics first.
Sure.
So my picture of mathematics is the mathematician has a bag and they're collecting theorems that they think are true and putting them in this bag.
Okay.
The mathematician with a finite mind only can have a finite bag of theorems that they kind of coherently think are true. But now, imagine that you put a false theorem in there. Well, now, in sort of from the Middle Ages, people have said, material implication, if you have a false premise, you can derive everything. This is this kind of idea of, principle of explosion or whatever, that once if you assume a falsehood, then then you can derive any possible result. So what happens to the mathematician when they put a false theorem in their bag? the answer is that false theorem entails all possible theorems, and so their bag explodes, and so their mind explodes in some sense. They can't maintain all these things together. So that's kind of the so now let's look at the quantum mechanics case. So now what I think happens is that the two photons, they go to slightly different places in physical space, but in branch shield space, these two photons that both could end up at the center of the screen are at kind of opposite ends of branch shield space. And so the observer, who is bounded in branch shield space, is trying very hard to say, well, what happened? You know, I could imagine both photons were there, but to imagine that, I would have to expand my mind in branch shield space. In fact, I would probably have to expand it in some idealized way infinitely. And so just like the mathematician can't put that falsehood into their bag, so similarly, the observer of these two photons can't conclude that they just can't make consistent the picture that the photon went through either one thing or the other. And so they have to say, the photon just disappeared, so to speak. But there are lots of, all these different phenomena of quantum mechanics. You can start to have, I think, almost intuitive kinds of views of what's going on there. I think to mention one from relativity that I think is very lovely. And by the way, there's an analogy in mathematics here as well. Time dilation in relativity. So, if you are an observer who's going faster, time to an observer, time appears to be progressing more slowly to an observer who's going faster. It's the phenomenon of time dilation. So in our models, you have a thing. It's represented by some sort of tangle in this network, and the thing is moving in this network. Well, the process of motion requires a certain amount of computation. You've got a thing in one place, it's got to reconstruct itself in another place. That takes a certain amount of computation. But the progression through time also takes a certain amount of computation. And the thing has a certain computation budget, so to speak, that is ultimately determined by the fundamental processing power of the universe, that's sort of the way of measuring distances in the Ruliad. And so what you end up with is you can either use your computational effort to sort of progress through time, or you can use it to rewrite your position in space. But as soon as you're rewriting your position in space, you're using up some of that budget, and so you don't get to evolve as quickly in time. And so you have to, that's why, that's sort of the mechanical reason that time dilation happens. So in the case of in mathematics, well, okay, let's see. There's sort of a similar phenomenon that has to do with if you were investigating something in one theory using another theory, like algebra and geometry. You're trying to use algebra, but you're studying geometry, and you're kind of going back and forth between algebra and geometry. There's this translation cost that, let's see, how does this work? Basically the time dilation phenomenon comes about because as you are trying to sort of think about geometry in terms of algebra, let's say, you are necessarily incurring you're slowing down your progress in geometry because you keep on having to do this translation back and forth to algebra. And I'm not untangling all the pieces to this quite right, but that I think there's a phenomenon there that is similar to time dilation, which is very weird. And by the way, these correspondences speak to sort of, help convince me that this picture that's sort of underneath both mathematics and physics is this same Ruliad. The fact that there are these correspondences makes that encouraging. I mean, another correspondence is that what is a black hole in mathematics? A black hole, I think, is a decidable theory. So just as in physics, there can be unbounded time, so in mathematics, there can be unbounded proofs. But by the time you have a decidable theory, the proofs are going to be bounded. And so that's like a decidable theory is like a black hole. And then you have in physical space, you have all these singularity theorems that say, when you have too high a density of energy and momentum, you inevitably form a black hole. In metamathematics, the statement would be when you have too high a density of proofs, you inevitably end up with a decidable theory. And so this leads to very bizarre things. Like, for example, the future of the universe may consist of a bunch of black holes. The future of mathematics may consist of a bunch of decidable theories. And in other words, that the sort of inexorable future of the universe sort of is similar to the future of mathematics, so to speak. Another thing correspondence between mathematics and physics is homogeneity in the physical world. That is, that we can move around, we believe that physics is kind of the same here as it is in the Andromeda Galaxy. In mathematics, the statement would be mathematics is kind of the same in the algebra place as it is in the geometry place. So in other words, there is an inevitable translation from one field of mathematics to another. If the mathematical universe is reasonably homogeneous, which I think I can argue that it is, then it is necessarily the case that there will be these correspondences between these very different areas of mathematics. And we see some evidence of this, of all these kind of dualities between different areas of mathematics and so on. But it's sort of interesting to see that homogeneity in physical space, the analogy to that is the presence of these things. And I think, by the way, in a recent thing that I've sort of come to imagine is that category theory, for example, which is one example of a kind of a broad sort of structural sort of description of lots of areas of mathematics. Category theory is a characterization of a so one feature of category theory is you say, oh, we apply this morphism, then we apply this morphism, and category theory says if you can apply this morphism, then that morphism, then there's always a morphism that just jumps all the way. That's just an axiom of category theory. That axiom kind of denies computational irreducibility, because if each of those morphisms was a computationally irreducible step, then to say, oh, but there's just a supermorphism that jumps all the way is to kind of say, but that there shouldn't be that supermorphism if you had to go through all these computationally irreducible steps. And so I think that that's in a sense, category theory is a description of computationally reducible is some kind of meta description of computationally reducible pieces of mathematics. But it's one of these things that I think is somehow there's a correspondence between that and this thinking about sort of homogeneity in mathematical space.
Time does fly, and this was terrific. Thank you so much again for talking with me, and hopefully our third round comes closer to the second than the second did to the first. Thanks again.
Yeah, it was great. Good stuff.